what? This is Mrs. Valletta. I wanted to go over the problem on spring potential energy and conservation of energy that was on the first quiz. Most of you did a pretty good job. You recognized that this was a positive displacement, so that the spring was stretched, and that the maximum spring potential energy was at the maximum displacement, which you can calculate is 1/2 times the spring potential energy times x squared. Now, we weren't given this spring potential energy, so we're going to have to calculate that. Almost all of you knew that the maximum kinetic energy was at the equilibrium, because what's happened is the spring energy has been transformed to kinetic energy. And most of you correctly figured out that the period was peak to peak or trough to trough, okay? And that we had a period of 1.4 seconds. Okay, just looking at the shape of it. Where some of you struggled was understanding how to figure out the spring constant. And the spring constant was actually straightforward. Remember, we know that the period is equal to 2 pi times the square root of the mass divided by k. And if you square both sides and rearrange for k, you can then plug in the mass, which we know, and the period, which we know from the graph, and you can get the spring constant, the number of newtons per meter that you need. And that should have come out to be 10.07 Newton meters. Again, if you don't know how to square this, you need to practice it. Then, of course, it's a simple matter of conservation of energy that we know that the maximum spring potential, which now that we have the spring constant and we know the displacement to be 1.6 meters, we can calculate, and that's 12.89 Newton meters, gets transformed to kinetic energy at the equilibrium. So there's no spring energy left. It's at the equilibrium, okay? And if you want to find the velocity, and you know the spring constant, and you know the total energy, then you can rearrange the formula to solve for the velocity. And remember, I recommended that you actually memorize this rearrangement. So the velocity equals 2 times the kinetic energy divided by the mass, and you take the square root of that, and that you'll come out to 7.18 meters per second. Finally, and this is where you seem to have a lot of trouble, is that I wanted you to tell me the velocity of the object at 0.8 meters from the equilibrium. Now, what I'm asking you to do is think about the fact that, yes, when we displaced it to 1.6 meters, we had 12.89 joules of energy stored in the spring. And you let go of it. And remember, springs, the further they displace, the more force there is. That means the more acceleration. So in a very short period, half of the distance that you've displaced it, you've taken more than half of the energy and you've converted it from spring potential energy into kinetic energy. And how do we know how much? Well, what's left in the spring is calculated, again, using the spring potential energy formula. So it's 1/2 times k that you've calculated above times where you are. And I'm using x squared to remind us that we're looking at a displacement of 1.8 meters. And when I do that, what I find is that I only have 3.224 Newton meters of energy left. So how much energy has been transformed? Well, that's simple math, 12.89 minus the 3.224, and we find that 9.666 joules of energy have been transformed to kinetic energy. And once again, we stick it back into our velocity formula, rearranged from the kinetic energy formula, and take the square root of everything. And what we get is that the 6.22 meters per second is the velocity of the object at that point. It's really just a simple conservation of energy problem, because you know that we've only done work up to 1.6 meters. Hope that helps. Look forward to seeing you. Bye now.